Hi, everybody. So, in this lesson here, just like it says here, we're going to look at an introduction to transformations and reflections. This is lesson two. The first lesson was a bit of a review of some preliminary material. So, here we're kind of jumping into the material and getting the course underway. So, a transformation, like it says right here, a transformation is a change that we make to the graph or relation of a function in the xy relation in the xy plane. And all the points that we're looking at are either going to be translated, which means they're going to be shifted left and right or up and down. We're going to change the shape, but not in a way that changes kind of the nature of the function. We're just going to stretch things. We're going to stretch things out either vertically or horizontally, or we're going to reflect the image of the function over an axis or a line. Now, for us, very specifically in this course, it's going to be mostly an axis. There is only really one line that we're going to look at. It's going to be the line y equals x, and we're going to talk about that in more detail later. Now, an invariant point, okay, and we want to make sure you understand about this because this is something that you're going to get asked about somewhat repeatedly to make sure that you understand it. It's a point for which the coordinates are unaltered by the transformation. So basically, what's going to happen here with these transformations is we're going to take a look at all of the collection of points on a graph. And what we're going to do is going to change those coordinates into another set of coordinates. And so one of the things that we're going to talk about here is our mapping. And we want to make sure that the mapping notation is clear and that you understand what's going on here. So with the mapping notation, what we're saying is this x and y, and this represents the old relation that we're looking at, is going to become a new set of x and y coordinates. And this little arrow is showing that we're going from the old to the new. And then what you're seeing inside that new x and new y, that's going to be what we're doing to the old one to make the new function here. We want you to use this as part of your communication here. Communication is very, very important. And being clear in your communication is really important. So like it says here, this refers to the arithmetic operations that we're going to perform to transform the original x and y into a new set of points. We're going to write them as a coordinate point becoming a coordinate point, okay? And we're going to use this to calculate the corresponding points. We're going to use this to find actual points on a graph. Okay, so what we're seeing here is actually what is happening to every point here. Now, another way that we talk about the transformations here is replacements and replacement notation. But when we talk about replacement, we're talking about replacing within the function notation. So the mapping has to do with the actual points on the graph. Oops. Well, it still doesn't want to do it. Hold on. I'm going to move this right out of the way here. The actual points on the graph. Whereas when we talk about replacements and replacement notation, I'm asking about what's going on with the function notation. And you're going to see as we move through this course here that these two often look like they're doing the opposite thing. And we'll explain that in a bit here. So what we're going to say here is this is going to tell us what we're doing to the x that we see in the function notation. So think about function notation. Think about function notation. What this is telling us is what's happening within the function. And then the y replacement out here, that is telling us, yoink, what's happening outside the function. Okay? And you're going to see in a little bit here, and I'll even just give this to you right now, that this replacing the x has a horizontal impact on the graph, while replacing the y with something has a vertical impact. I'll take a look at that in more detail in just a little bit. And like it says here, we're going to do x and y here separately, basically because they show up separately in the function notation. Whereas when we talk about the mapping notation, we're putting them together as the point, okay? Because we're creating one point. It's got the two coordinates with it, but we got the one point there. So there's two different things that we're looking at here. There's mapping notation and then there's replacement notation. Then we're going to look at the actual equation of the transformed function here. So initially, when I made this video, I kind of skipped over this section about the equation a little bit quickly. But it was afterwards that I realized, no, I really do need to go back and look at this. And I don't want to spend a ton of time on this because the idea of creating the equation is actually going to get fleshed out a little bit more as we go through this. But I do want to take a look at an example here. Let's take a look, for example, just at this first one. So what we're saying here is can the equation can be the equation of a specific function or a graph. So it can look something like this, or it can be in general. It can be expressed just in terms of how we're manipulating the function without any reference to a specific function. Now, what I want to do though is I have noticed after working with some students here that the connection between these two and maybe what specifically this means wasn't clear. So let's just take a look at the example that you've got here. Although you can write a function like this, and you can write how a function's been changed like this, let's just say, just for argument's sake, that what I want you to do here, the f of x here is 3x minus 2. Like that is the function. And now I'm changing it to become this. I want to talk about what's going on here. What this means is that the independent variable in the function is being replaced with 2x. Okay, so when I've got f of x, and let's just do it like this. When I've got f of x is equal to 3x minus 2, if I get rid of the x and put 2x in here, that means I'm getting rid of the x here and putting a 2x there. And then when I multiply the function out front by 3, that means in front of the whole function here, I'm putting a 3. And now when I evaluate this, that 3 times f of 2x becomes, well, 3 times 3 is 9 times 2 is 18x. And then the 3 gets distributed to the negative 2, so it becomes negative 6. And so that y equals 3 f of 2x, if the function is this 3x minus 2, then becomes this 18x minus 6. Now, that was not the intention of this little section here, but like I said, I've noticed that there's a bit of a misunderstanding as to how to actually apply the function notation. Okay, so now let's take a look at a very specific transformation here. We're going to look at a reflection. So a reflection is a transformation that reflects a graph in an axis. Now, for our purposes here, for the most part, it is going to be an axis. Or I will put this here, or we're also going to look at reflecting over the line equals x, y equals x. You can reflect over other lines, but those are the two that we're going to focus on in this course. And so what we're doing is we're creating, like it says here, a mirror image of the graph across that line, and that'll be the line of symmetry. And you might remember that from an earlier course when you were looking at quadratics, this line of symmetry. Now, think about it like this. Like if you look at the diagram here, the r is getting reflected over the x-axis. I want you to think about where invariant points might be in a reflection. Okay, so if I'm flipping this thing over the x-axis, for right now, all of the points have changed. Every point on that r has changed. But that r could have been resting right on the x-axis. And if you had a point resting on the x-axis and we flipped it over the x-axis, that point would have stayed the same. And there's a really good reason for that. Okay, but that becomes those invariant points. And there are any points that end up being on that line of symmetry or on that line that we're reflecting it over. Now, a vertical reflection is going to be one such that the x-axis is the mirror. Now, you gotta watch out for that. That can be a little bit tricky for people to get their heads wrapped around this. This is a vertical reflection, but it's the x-axis that's our mirror, not the y-axis. Okay, the x-axis. And what's happening here is that all of the y coordinates are basically switching signs. The x coordinates are staying the same, but the y coordinates are changing. So here's what's going on here. Our original function, y equals f of x, what we're going to do to that function is we're going to replace the y with a negative y. Okay, so in the function, I'm making that replacement. Okay, so this negative y goes over here. Now, that's going to end up looking like this. Instead of a y equals f of x, it's going to be negative y equals f of x. After we make that change, though, it is customary for us to basically isolate the y. We don't usually look at functions where there's a bunch of stuff going on, multiplied, divided by the y. We isolate the y. So I'm going to typically bring that negative over. And notice where it sits. It sits outside the function. Okay, outside the function, we're going to see this repeatedly, is vertical. Anything that's affecting the function, but it sits on the outside, is going to cause a vertical change here. Now, on our mapping, what's happening here is every point x comma y on the original simply becomes x comma negative y. Essentially what we're doing is we're changing the sign on the y coordinate. Now, think about this. What number doesn't change if you put a negative in front? You probably notice after a moment of reflection, well, it's going to be 0. Yeah, so if the y coordinate is 0, plugging a negative in front of it isn't going to change anything, which means those points are going to be invariant. So it's going to be points that look like this, x comma 0, and these are our x-intercepts. Those are the points that will not change once you perform a vertical reflection. Okay, now, horizontal reflection. In this case, it's the y-axis that's the mirror. And again, that can be a little confusing for people because it's the horizontal reflection, but it's the y-axis that's our mirror. So any point that shows up on the y-axis is going to be invariant. So here, what we're going to do is we're going to take that x-coordinate inside, or that x variable inside the function, and we're going to replace it with negative x. We're going to change its sign. Now, when we do that, that means we take the x out of the function and we put negative x in. But notice we leave the negative there. We're not going to move the x to the other side because the y is already isolated. It's already in a form that I like. I just now have a negative in front of the x. Okay? And so that's how we're going to leave it here. And so what we've done here is our points here are x comma y, and those represent all of the points on the original graph, simply become negative x comma y here. We are changing the sign on x. And because this is inside the function, okay, because the change that we're seeing is inside the function, because it happens before the function acts on it, this is changing the value of x before we apply the function, it's horizontal. It's causing a horizontal change to the graph here. And just like before, as long when that x-coordinate is 0, putting a negative in front isn't going to change anything. So it means all of our invariant points are going to look like this, 0 comma y, and those correspond to y-intercepts. Okay, so now let's take a moment and look at some examples. Now this question says, given y equals f of x, complete the table and sketch the graph and identify the invariant points. But we're looking at this transformation right here. Notice that the negative is inside the function, so I know that this is going to be a horizontal change to the function. And in particular, I know this is going to be a horizontal reflection over the y-axis. Okay, so I know that the image point here is going to mean we're changing the x to negative x. And then the y stays the same. So we're going to use the mapping notation to help us build all of the points here. And really all that the point is telling us to do, the image point, is to change the sign on the x. So this becomes 5, 6, 2, negative 2. Oh, look at this one. 0, negative 2. Well, putting a negative in front of the 0 does nothing, so that becomes 0, negative 2. That's my invariant point. And this point becomes negative 2, 0. This will become negative 3, 1. And this will become negative 5, 0. So now plotting these points, 5, 6 is going to be over here. Okay, and notice how that is really just that point flipped over. The point 2, negative 2 is really just that point flipped over. And from there, you can see each point going on and on here, except notice that 0, negative 2 stays right there. That one doesn't go anywhere. But our point 2, 0 becomes negative 2, 0. So that point flips over. The point 3, 1 becomes a point negative 3, 1. So that point flips over. And then over here, 5, 0 goes way over here to negative 5, 0. And now we just connect the dots. And actually, I'm going to use red here because it's got a little, I've got it set a little thicker. And then we just connect the dots. And this is our other graph there that we flipped. Perfect. And we've identified the invariant point. The invariant point that occurred at 0, negative 2. Now let's do this one here. Sketch the graph of y equals negative f of x. Now notice this is outside, so this is going to be a vertical reflection, okay, over the x-axis. My invariant points are going to be the points on the x-axis, and I can just read those right off. That is going to be those points, negative 3, 0, and the point 1, 0. Wonderful. Now, I can be kind of lazy here. There's really only one point that I need to flip, and that's that point, that vertex here, so negative 1, 2, and it is going to drop down here over the x-axis to become the point negative 1, negative 2. And then because I know the invariant points stay the same, I can simply connect the dots here, going out like that, and going out like that. But remember, you need to put the little arrows on there. Just want to remind you that we're going to be expecting you to put the arrows there because those lines go on and on. Okay? Hopefully that makes sense. So given that the point negative 5, 4 lies on the graph of the function y equals f of x, state the coordinates of the corresponding point and the type of reflection it is. Okay, so first of all, look at this first one. Because we've got the negative outside, first we know that this is going to be a vertical reflection. Okay, and so this is going to be over the x-axis. And we know that what that does is change the y-coordinate sign. So the point negative 5, 4 is going to become the point negative 5, negative 4. For the second one here, because the negative is inside the function, we know that this is going to be a horizontal reflection. Okay, it's going to be over the y-axis, which means my x, y, and my mapping is going to become the point negative x, y. It's just going to change the sign. So negative 5, 4 is going to become the point 5, 4. And then here, because we've got both of those negatives, inside and outside, this is both a vertical and horizontal, both a vertical and a horizontal reflection. So we've got both here. So we can put those together in our mapping point, x, y, and basically both of those coordinates are going to change signs here. So negative 5, 4 is going to become the point 5, negative 4. There we go. Let's take a look at the next one here. It says, given the point negative 3, negative 6, and it lies on the graph of the transformed function, state the corresponding point on the original function. So in other words, we want you to go backwards. We want you to undo this. So this is a horizontal reflection. So it's changing the sign of the x coordinate. And really what's happened here is we've got the point negative 3, negative 6 here, and I want you to go backwards. Now, for this particular question, I don't think that's particularly hard to see what's going on here, okay? But these are going to get more complicated as we go. And so one of the things that we might do here is we might say, okay, right now as it stands, I know that that negative x is equal to negative 3. Like we can see right now that the y coordinate didn't change, but the x one did. If I bring that negative over and solve for the original x, I get x is equal to 3. It's just as easy as that. As they get more and more complicated, doing it like this, setting up that little equation and solving for x is going to make that a little bit easier. When they get more complicated, right now you probably could have just seen what was going on right there. So how do you determine the equation of a transformed function? Well, what we're going to do here is you're going to identify the replacements. Okay, you're going to identify the replacements. What we want you to do here is we want you to update the function. Okay, so you get your function notation, update your function notation. So identify the replacements. For example, in the previous question, I knew that we were replacing x with negative x. So in my function, it becomes f of negative x. And then what we do is we're going to translate the function notation into an equation. And that's something that we were looking at a little bit earlier in this lesson. I took a kind of an aside there and talked a little bit more about that. Okay. So let's take a look at a couple more here. So given the function f of x equals the square root of 3x minus 5, write the equation of the transformed function if it's reflected in the line y equals 0. Okay, So y equals 0, remember, this is the x-axis. And so if I'm reflecting this over the x-axis, I am replacing y with negative y, which means this is going to be, so y equals f of x becomes negative y equals f of x, or y equals negative f of x. And now what I'm going to do is put the original function back in there. Oh, sorry, I just want to clean that up there. And so y is going to equal negative square root of 3x minus 5. And then because it's in front of the function, I'm going to distribute it to the whole thing. So it's going to be negative 3x plus 5. That's my final function there. If f of x is reflected in the line x equals 0, bear in mind, this is the y-axis. And so what this means is I am replacing x with negative x. So y equals f of x is going to become y equals f of negative x. That's exactly what that means. And now I translate that back into the equation here. So my independent variable x has been replaced with negative x. So what I've got here is y equals the square root of 3 times negative x minus 5. Just that one little part there changed. And so this becomes the square root of negative 3x minus 5. And that's the answer we're looking for here. Very, very common mistake would be to make that the square root of 3 minus x minus 5. The 3 is being multiplied by the x in the original expression. So when I do that here, whatever I replace it with needs to be multiplied by the 3 as well. So just watch out for little things like that. Make a big difference. And then last but not least, in this lesson here, if the function is f of x is equal to 5x plus 2, and g of x is equal to negative 5x plus 2, this is a reflection how? Okay, so you might want to pause right now and just give this a little bit of thought. Now let's go through and just take a look at this, if you've had a moment here. If it was a reflection in the x-axis, if I was to reflect it in the x-axis, I would have replaced y with negative y. And so this would have become negative y is equal to 5x plus 2. And then when I bring the negative over, it's negative 5x, and that's great, that's what I see. But the negative distributes to the 2 as well. So if it was a reflection in the x-axis, everything would have changed signs. If it's a reflection in the y-axis, I'm going to replace x with negative x, which means we're going to get 5 times negative x plus 2. And then I'm going to multiply that together to get negative 5x plus 2. And that is actually what I'm seeing, okay? So that's as far as I need to go. It was just the term that had the x in it that changes. The reason why this is a good question is because sometimes we inadvertently create a wrong rule where we think, well, if there's a negative in front, that must mean it's been reflected over the x-axis. That's only true if all of the signs have changed, right? If only the terms with the x in it have changed signs, then that's likely a reflection over the y-axis. Now, there are some other things you got to consider there, but this is a good place to start.